Hello all, welcome to problem 3 of the Stat 111 2019 final exam live solve. Yeah, this is problem 3. As usual, I encourage you guys to all go through this problem, maybe try to work some of the parts out and at least read the problem before coming back to this video for the solution. So let's get into it. This is a linear regression problem. So a perennial challenge that occurs in the evaluation of new treatments is the test-retest conundrum. Suppose that a group of n children are given a math test at age 9 and another at age 10. Let xj be the score of the math test at age 9 and yj be the score of the math test at age 10 for child j. Let the correlation between xj and yj be rho with rho between 0 and 1, strictly between those two. And suppose that yj, xj, the pair is distributed IID. We're going to have a few definitions. Let sxx be this, syy be this, sxy be sort of a correlation looking thing. And we have r is equal to this sxy square root sxx syy, the sample correlation. So part A, ask for the estimated slope beta hat for a linear regression of age 10 results on age 9 test results in terms of R, SXX, and SYY. So we have a form for this in the notes. So it's beta hat 1 is going to be equal to SXY over SXX. So we need to get this in terms of SXX and S, like we just need to get rid of this guy. So one way to do that is to look at the problem and we see this. So here we can get SXY equal to R square root SXX SYY. So we're going to use this down here. So we have that this is equal to R square root SXX SYY over SXX. And then we have our square root SYY over SXX. We can divide out this top SXX into the bottom. So that's going to be part A. Now for part B, define y hat j is equal to this like linear regression looking thing with this on here and show that this is a thing. So we're going to want to just plug in. So we have beta hat naught is equal to y hat j minus beta hat 1 xj. And similarly, we're going to also have, like if we take the mean of everything, we're going to get like, so let's go, for example, let's take like y, so we're going to get like sum of y 1 over n. So this is going to equal 1 over n sum of like beta naught hat plus beta 1 hat xj. And this is going to equal beta naught hat plus beta 1 hat x bar. So we get y bar is equal to that. So we're going to get beta naught is equal to y bar minus x beta 1 hat x bar. And then now we can replace some stuff. So we can replace this, we can go into here and we have, we're going to go yi or yj hat minus y bar over square root syy over n. This is going to equal to, y bar minus we're going to get beta hat naught plus beta 1 hat xj there. minus y bar, square root SYY over n. And this is going to equal beta not, I forgot to put a hat there. We're going to be able to replace that beta not hat with the y bar minus this x bar. And then we have plus beta 1 hat xj minus y bar. And then we're going to be able to cancel these guys out, and we get beta 1 hat xj minus x bar over square root SYY over n. And then from the stuff in A, see if this will let me move it. From the stuff in A, which is this this right here, that's what this is, beta 1 hat. We get this is r square root SYY over SXX. And then we're going to multiply this by xj minus x hat, or x bar, in the denominator SYY over n. And then we're going to cancel out these SYYs, and we get equal r xj minus x bar square root SXX over n. And that is exactly this right-hand side. Okay, so that is B. Moving on to C. Let's move some stuff. So suppose you've developed a new computerized math intervention. To test your intervention, you consider conducting a test-retest study. You test the children's math ability at 9, provide the computerized math intervention to all of the children, and you do a retest of them at age 10, and we have the data xj, yj, xj satisfying the same assumptions. What is the predicted score at age 10 for a child who scored 2 standard deviations below the mean at age 9? So we can use like a few of these guys. So if you look at this stuff in part B, this is the standardized test score, right? Like, so if this person, so if person xj, like, or I guess a new individual x prime or something, scored below, scored 2 standard deviations below the mean at age 9, then this guy here is going to be 2, negative 2. So we are going to get that. So this is going to be negative 2, and this is going to be negative 2r. So we get that as the number of standard deviations below the mean that other person is. So we're going to get a prediction. I guess I'm going to sort of rewrite that. So we get xj hat, the predicted, minus y bar over square root SYY over n. This is going to equal negative 2r. We're going to unstandardize it, get this prediction, and it's going to go negative 2r square root SYY over n, and then we're going to add this y bar. So this is going to be our predicted value. Okay, and this is like a little bit more, or a little bit less than 2 standard deviations under the mean of age 10, because this is the age 10 standard deviation, or the age 10 value, and this is negative 2, this would be the 2 standard deviations, but we're going to mute it a little bit by r, the sample correlation. So intuitively, why is this not 2 standard deviations below the mean at age 10? And that's going to be regression towards the mean. And intuitively, that is, if so, 2 standard deviations below the mean is quite low. That's a pretty extreme value. We would expect that these students are going to do a little better just out of like randomness and extremity than 2 standard deviations below the mean exactly. So they're going to perhaps, yeah, we would see that these students are probably going to show some improvement rather than just stay exactly stagnant. These extremes are going to get drawn in a little bit in the next iteration. That is the retesting at age 10. Okay, and then finally use potential outcomes notation to explain a policy to a policymaker whether using test retest will allow them to make a causal effect of the new computerized math intervention. So our potential outcomes are going to be YJ1 and YJ0. This is the potential outcome in the alternate universe where we give the intervention. And then this is going to be the causal impact of the result in the world that we do not give intervention. So in this case, we observe all of these at age 10, but we observe none of these. So overall, we're going to see, we're not going to be able to estimate any of these because we simply have not seen any of these alternate universes, but we've seen all of these. Generally in the causal world, we're going to want to randomly assign to like control group and treatment group. And then this random assignment will allow us to infer this value and this value, which will allow us to get the causal, infer the causal effect. However, in this case, we have only we've assigned everyone into the treatment group. So we're not able to approximate this, and therefore we cannot approximate the effect, which would be this minus this for that student in particular. So that's problem 3. Thanks for watching as usual, and I will see you guys in problem 4. And good luck studying for the final.